oil rig in the Gulf is held steady at its designated drilling location by 3 tugboats. Tugboat A pulls with 52,000 Newton straight in the easterly direction. Tugboat B pulls at an angle of 38 degrees, north of west. Tugboat C pulls 43 degrees west of south. Draw a proper free-body diagram, and then find the magnitude of the tension of the ropes attached to tugboats B and C. So let us call all the tensions just A, B, and C, and we can already state that we know that the tension A equals 52,000 Newton, B and C is what we need to find. We do know that theta B equals 38 degrees and theta C equals 43 degrees. So the very first thing we need to do is draw a free body diagram of the situation. So let's do this. Let's define axes first. Let me define this here as the positive y-axis, and let me define this here as the positive x-axis. Now let's draw in the forces. A is to the right, so this is the tension A. This is tension B, and this is tension C. And we know the angles are these here. This is the angle theta C. This here is the angle theta B. We see that A is strictly along the x-axis, but B and C both have x and y components. So we need to find these components. This here is the y component of B, and this is the x component of B. Likewise, this is the y component of C, and this is the x component of C. So if we look at the components, we have to be very careful now which one is adjacent, which one is opposite. And then we also have to be careful about the signs of it. Let's start with x. The x component of A, that is just the magnitude of the vector A, because A is just in the x direction. And then that follows right away also the y component of A is 0. That's correct. The x component of B, now you have to look carefully. B points x in the negative direction, so it is minus the magnitude of B. Dx is adjacent to the angle theta B, so it is times the cosine of theta B. The y component of B is upwards, so this is positive B, and it's opposite to the angle, so it is the sine of theta B. The x component of C, that is also negative, the magnitude of C. Now we have to be careful because the x component of C is opposite to the angle theta C. That means it is the sine. So don't get misled that x is always cosine. You have to be carefully looking at whether this is opposite or adjacent to it. Then Cy, of course, is then also negative. See, it points also down in the y direction. C, and the y is adjacent, so times the cosine of theta C. We have found all the components. Next thing we need to do is we need to apply Newton's laws. This is all in a steady state, so we have the sum over all forces in the x direction equals the mass of the drilling rig times AX. But it's held steady, so AX equals 0. Likewise for the sum over all forces in the y direction equals MAY, but also AY is 0. That is because it's held steady. So if we want to look at all the forces in the x direction, we just have then AX plus EX plus CX, and that is 0 because AX equals 0. Likewise, AY plus BY plus CY equals 0. Let me plug in now all the components. In the x direction we get AX, which is just A. BX is minus B times cosine theta B. CX equals minus C times sine theta C. And that equals 0. This is our first equation. Our second equation that we find comes from the y direction. AY is 0, BY is just B times sine theta B minus C times cosine theta C, and that equals 0. So we have now two equations, and there are two things which are unknown, the magnitudes B and C. Everything else is known. We know A and we know the two angles. Two equations, two unknown, so we should be able to solve that. The first thing that I'm going to do right now is I take the equation number 2 and I'm going to solve that for one of the two unknown magnitudes. So from 2 it follows that B times sine theta B equals C times cosine theta C. So all I did is I brought the term with C to the right hand side of the equation. Now I'm going to solve that, for example, for the magnitude of C, which is unknown. So C equals B times sine theta B over cosine theta C. This seems not too hard yet, but because we neither know B nor C. But now I can take this and I can substitute this, so I put this into the equation 1. If I do that, I eliminate the unknown magnitude C, and equation 1 will be left with one unknown, that is B. We can solve for B. So if I do this, I find that A minus B times cosine of theta B minus, and instead of C I write now B times sine theta B over cosine theta C. That is the variable C, and in equation 1 we had C times the sine of theta C, and that has to be 0. Now we have one equation. The only thing we don't know in this equation is the variable B, attention B. Note here that, different color, theta c divided by cosine theta c. This is just the tangents of theta c. So let me rewrite this equation. I find now that a minus b, we have minus b times cosine theta b, and we had minus b times the sine of theta b times the tangents of theta c, and that is 0. From that it follows now that a equals b, I bring this over to the right hand side, times cosine theta b plus the sine of theta b times the tangents of theta c equals 0. We have that already. Sorry, let me put this out here. There we go. And now we already get our expression for b. It is just the magnitude of a divided by the cosine of theta b plus the sine of theta b times the tangents of theta c. So this is 52,000 Newton divided by the cosine. Theta b was 38 degrees plus the sine of 38 degrees times the tangents of 43 degrees, and what we get now is 38,175 Newton. Let's call this 38,200 Newton. So we have B. Of course, now we can also directly calculate what C is. I challenge you to show that C equals A divided by the cotangents of theta b times the cosine of theta c plus the